We may have discussed this in class, but I want to take some time to go over some of the key concepts one more time. First off, if it's a prepare question and you see multiple arrows, that basically means that this is multiple steps. Multiple steps. I usually do write that, but just to clarify. All right. You have an aldehyde here. You have total 4 carbon atoms, and those 4 are right here. We have added another carbon atom, so let's call it 5th, and then we have added 2 carbons and 1 oxygen. So one thing that we learned in class was that an alkyl group can be added using a Grignard reagent. So the first thing I would do is treat this with methyl magnesium bromide, follow it with hydrolysis, and that should give you, it's an aldehyde, so that should give you a secondary alcohol. Now, once you have generated the secondary alcohol, you have to now replace that OH and add 2 carbons and 1 oxygen. How can you do that? We learned in class in chapter 18 that that can be done if you treat it with an epoxide, because an epoxide is 2 carbons and 1 oxygen. But the ring opening has to be done if this particular carbon atom has a more carbon ion-like character, because realize between oxygen and carbon, oxygen is electronegative, and so that makes carbon more positive. That means somehow I have to generate a carbon ion-like character at that particular carbon. How can we do that? Well, we know that Grignard reagents do have alkyl chains having a carbon ion-like character, but in order to get a Grignard reagent out of this alcohol, you first will have to convert it into an alkyl halide. So how about treating that with PBr3, which will give you a Br, and then I can subject that to magnesium ether, 0 degrees Celsius. That gives you MgBr. We have set the stage that this is negative now. That negative is going to attack, ring will open, and after hydrolysis, it will give you the choice, or the compound of your choice, so 6 and 7. All right, let's take a look at another one. We have the following. We have an aldehyde, and we have a primary alcohol, and we have total, let's see, 1, 2, 3, 4, and 5. And here I have 1, 2, 3, 4, and 5. That means I'm adding this 2 carbon chain somehow. So again, there will have to be a Grignard reaction, and you know that the Grignard reaction has to be done at an aldehyde. We know that already. But between the 2 oxygens, there's 1 oxygen right here, there's another oxygen for the alcohol, but one of them has to go. That means either you have to carry out some kind of a dehydration or convert that OH into a better leaving group so we can ring close. So let's take a look how we can go about this. And there is no one way, there are multiple methods, but one of the ways is, or could be, if you treat it with thionyl chloride. And of course you can use PBr3, you can use PCl5, any one of those, to essentially create a Cl at position 5. That then will be treated with ethyl magnesium bromide, followed by hydrolysis. So you are going to end up with an alcohol with an ethyl group. Now notice I have all the carbons, 4 and 5, and maybe we can call it 6 and 7. I have all the carbons. The only thing that needs to be done is somehow if this oxygen attacks at position 5 and chlorine then will leave because it's a good leaving group. So it's a good idea if we could somehow get rid of that one proton. By the way, this point of attachment is oxygen. Almost seems like it's hydrogen. It's oxygen, that's the point of attachment. So if somehow I can get rid of this H, I should be in business in converting this compound to the cycle. How can we go about that? How about treating this with sodium hydride? Sodium hydride is a base that's going to get rid of the acidic proton and generate the alkoxide. Let's just show that. Picks up the proton, electrons move on oxygen. So you actually end up getting O with a negative and a Cl. And that's going to attack the primary carbon to generate the six-membered ring that we desire. All right, let's go forward. Oh, by the way, if instead of Cl you wanted to use a different leaving group, so if you wanted to convert the OH into maybe the tosyl, OTS, that's okay too, because that's a good leaving group too. So any good leaving group will work in this case. Okay, I'm jumping back to slide number 1 because I've missed these two for some reason. The question is you have to synthesize cyclohexene from methoxycyclohexane. So that's right here. And that's a pretty straightforward question. You will first treat this with HI or HBr and you will heat it. So hopefully you can see that the protonation will take place. And now when it's time to cleave the bond, essentially the I will come from the least substituted site. So you're going to end up with cyclohexanol and methyl iodide. And then you can convert the alcohol into the alkene simply by concentrated H2SO4 or POCl3 pyridine. So that's a very straightforward method to do that. This could be a part of a box problem as well, so just keep an eye on that. The next question is using Williamson synthesis, prepare ethoxybenzene. So ethoxybenzene is this right here. Recall methoxybenzene is anisole. So that's methoxy, this is ethoxy. We have to work with ethoxy in this particular one, so I'm going to erase this anisole guy. But you have to prepare that from your choice of alcohol and alkyl halide. This is exactly from what we did in lecture actually, where I told you that since it's easier to get rid of the proton from phenol because those are more acidic, and the product is resonance stabilized, you're going to begin with phenol. You'll treat it with sodium hydride, get sodium phenoxide, treat it with ethyl iodide or bromide, whichever you want to. Attack occurs, SN2. Gives you the product. All right, the next question is that you have to convert styrene, this guy, into ethanol, and it's 2-methoxy, 1-phenyl, 2-methoxy. So hopefully you can see this 1 and 2. 1-phenyl, ethanol is the one that decides since it's 1-ethanol. In case of ethanol, you don't have to specify that 1 because automatically, implicitly, that's where you would start numbering. So hopefully you can see that there are 2 oxygens, and we discussed that umpteen number of times. There are 2 oxygens. That means there is an epoxide which will need to be cleaved. Now you have to begin with styrene, and in order to get an epoxide from there, you have to obviously treat that with MCPBA. Your solvent for this reaction is dichloromethane CH2Cl2, and that gives you the epoxide. Now, realize in this particular case, you have to ring open in such a manner, like I'm trying to compare the structure with my structure. So you have the phenyl and the OH on the same carbon. So you have to ring open in such a manner such that the OMe is on the carbon away from the benzene ring. What that means is that it's the least substituted carbon that must go through the attack. And so what does that tell you? That tells you that you should not use methanol and acid, because acid is going to ring open from the most substituted site, and you don't want that. You want the opposite. You want the least substituted site to get affected, and that should be the one which should ring open and get cleaved. And so in this particular case, you should treat it with a base. So a nucleophile such as CH3O minus Na plus, that is going to attack at the least substituted site, and it will generate O negative, OCH3, and that negative charge will then be quenched by protonation, and you will get your desired OMe and OH. So that's 1-phenyl 2-methoxy, which is same as the desired product. All right, let's go forward. We have some more questions. Some of these questions are actually from some previous exams. One of this is the wiki that we were not able to go through in class because the student was absent. So I wanted to take the time to go over those questions so you get the exposure. The question is, write the complete mechanism for conversion of 2,4-dimethyl-pentane 1-ol into blah, 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 blah. Let's just first see what these structures are. It says that it's 2,4-dimethylpentane, so let's draw pentane first, and 2 and 4-dimethylpentane. And on that, I'm supposed to put at position 1, I'm supposed to put 1, 2, 3, 4, and 5. I'm supposed to put an oxygen. And on that oxygen, I have again 1, 2, 3, 4, 5, 2, 4 dimethyl pentyloxy or pentoxy. So notice this is a symmetrical ether. So anytime you have symmetrical ether, you don't have to really go the Williamson ether synthesis route. You can simply take the alcohol and dehydrate it. So the alcohol in this case, and here they're saying that you have to begin with the 2,4-dimethylpentanol. So we are given pretty clearly that this is our starting alcohol, and we have to subject this to treatment with acid. We know that. And we would heat it, and it would give you the product. Let's take a look how, because they're asking for a complete mechanism. So H2SO4, will pick up the proton, oxygen goes through protonation, gives you the positive charge, HSO4 negative gets generated. And now this is similar to what we did in class when I asked you, should water leave and then the attack from the other alcohol should take place? Or is it that the alcohol attacks first and then water should leave? And it's the second case recall from class. And the reason for that is that this particular carbon atom holding the water is a primary carbon center, and you can never show a primary carbocation in that spot, hands down. That's the rule. It is going to go through an SN2, and so the OH is going to attack first, and then water is going to leave. So that will give you your oxygen, still has the hydrogen, and then positive charge as well. And then the bisulfate is going to come by, pick up that proton, and you will end up with the desired symmetrical ether. So the key thing here is basically the sequence in which you show your mechanism, whether you're showing the alcohol attack first and then water leave, or you're actually showing a primary carbocation which is not very stable, is never going to get formed. Okay, let's go forward. I accidentally missed. Okay, the question is, ethers in general have lower boiling points than their corresponding functional group partners, alcohols. And that's a question we've discussed umpteen number of times. Ethers only suffer of dipole-dipole forces of interaction, whereas alcohols have hydrogen bonding. So that's why they're more polar, and require greater amount of energy, to break the bond, the forces of interaction between two alcohol units. And that's the reason you would see higher boiling points in case of the alcohols as compared to ethers. And if you compare that to alkanes, alkanes actually will have least boiling point because they would have only London dispersion forces, which are weakest and easiest to break. So hopefully that makes sense to everybody. I've discussed that umpteen number of times. But if you still have a question, feel free to drop by or send an email. All right, let's take a look at an NMR question. Even though I told you there may not be some direct questions within the exam, you could see a bonus based on, NMR. But like we discussed day one of class, the beginning point is to get your degree of unsaturation. And in this case, it's going to be 10 minus 7 over 2 plus 1, because the formula is carbon minus hydrogen over 2. Oxygen doesn't count, and you add 1 to that. So that comes out to be 4. And anytime I see 4, I think about benzene ring, and that is 4. And so I'm seeking that there should be a peak at 7. Guess what I do? And that's worth 5 protons. That means it's a mono-substituted benzene ring. Now you have only 3 other environments. One which is a doublet, and the other which is a septet. Again, for me, anytime I see a doublet and a septet, I'm thinking of an isopropyl group because these two are identical. They split the one hydrogen over here 7 times, and because 6 plus 1 is 7, and this one hydrogen splits both of these methyls. That is why it's 6 protons as a doublet, and so there has to be an isopropyl group. And then you have to think about what comes for the 4.8. That is a singlet. It is worth only 2 protons. So when you do the math for how much you already have, you have the C6H5 for the benzene, you have the CH, and you have 2 CH3s. So when you do the counting, you basically are left with a CH2. So the question is whether you should place the CH2 and then oxygen with the isopropyl unit, or should you place the oxygen first and then the benzene and then so isobutyl, essentially isobutyl phenyl ether, or is it isopropyl benzyl ether? And the answer lies that it is the first one. The answer to that lies in the fact that, notice the CH2, the benzylic hydrogens, if those were present has the completely blue structure, then you should have seen splitting over here as well. So this guy should have been shown as a doublet, and we didn't see that. And you should have seen, instead of septet, you should have seen like a multiplet, like a big splitting pattern, and you don't see that. So this is not the correct structure. My benzyl ether, the benzyl isopropyl ether, that is the correct answer to this question. All right, here are some box problems. And again, these are from previous exams, but I just thought to go over some of those. I know we've done umpteen number of these in class, but to see them, kind of put together, that's a different experience altogether. So I just thought I'll put something together. So I have here, what kind of an alcohol is that? It's a tertiary alcohol. And so you know that for a tertiary alcohol, if they're asking for a carbonyl, that means it has to go through a ketone. And so there are two possibilities. You could either have the symmetric ketone, in which case the rest of it, that means right from over here, this part is going to come from the Grignard reagent. The Grignard reagent will look like the benzene ring, CH2, Mg, and Br, so that this negative part is the one that attacks over here, and after hydrolysis you get your product. What that means is that the alkyl halide minus the magnesium should look like the bromine. On the contrary, if you don't want that, another possibility is that your ketone is right over here, and on the other side you have a benzyl group. That would mean that your Grignard reagent is a 2-carbon chain, and so ethyl bromide is what you're going to begin with. So either of the two answers is a good answer for that question, or a similar question. But notice we kind of backtracked. We went in the opposite direction because we were given the product, so it was retrosynthetic analysis, and I went with what they expected. So it's a good idea to read the information given for that box. Let's see if we can apply more concepts on some of these problems. It's given here that we have ethanol, and we are subjecting that to sodium dichromate in cold. So that should tell you that it should give you an aldehyde because it's not hot. So it's not going to go all the way to carboxylic acid, but will stop at the aldehyde level. And the other clue is that I'm treating that with a Grignard reagent. That means it has to be a carbonyl compound. Notice I have 1 and 2 carbon, and I have 3, 4, 5, and 6 carbon. So an aldehyde gives you a secondary alcohol. Those are my 2 carbons, 1 and 2. 1, 2, 3, 4. So I have my 3, 4, 5, and 6. Now, I'm supposed to use sodium borohydride. That's a reducing agent. Reducing agent will give you the alcohol back. And it's saying that Jones reagent gives you something which gives you NMR peaks and is used in salad dressing. I wonder. Just in case you forgot, Jones reagent is going to go all the way to the carboxylic acid. So you're going to end up with acetic acid, CH3, C double bond O, OH. Now, once you have your alcohol, POCl3 pyridine, that's a dehydrating agent. So that's going to give you your alkene because you're removing OH and you're removing H from the neighboring carbon, from the beta carbon. MCPBA gives you epoxide. So you're supposed to get an epoxide first. And then we are treating that with hydronium, that means that epoxide is going to ring open. It's going to give you the transdiol. We treat that with PCC, so that will give you 2 aldehydes. Alright. We are also given that if alcohol is A, then 2 moles of A with concentrated H2SO4. Hopefully you can see it's a method to create the ether, the symmetrical ethers, and it's given that it's a slightly polar, inert, low boiling flammable solvent, and they gave you the proton NMR that it's a triplet and a quartet, so that should give you information that there should be ethyl groups on both sides. So that's how I would solve it. Let's see. I have been given another one. So you're given the starting material. Those are real bonds. It's just dashed. That means it's pointing backwards. And I'm treating that with PBr3. Notice all that's going to happen in that entire big chunk is that the OH is going to be replaced by bromine. And since it's an SN2, that bromine should point towards us. That means you're going to draw it as benzene, 5-membered ring, dashed methyl, solid bromine. So far so good? Okay, let's do this. Negative charge, positive charge. It's an SN2, so again it's a double inversion. I'm going to begin with benzene, 5-membered ring, methyl group still where it is, dash line, OCH2CH3. Since that is going to be my nucleophile, bromine will have to leave. Now if you do that with the tosyl chloride, so this is TSCl, benzene remains intact, 5-membered ring, methyl, realize, is not changing, that's going to stay where it is. Now tosyl is going to break the OH bond, so it's OTS. If you wanted to show the whole thing, of course, you're welcome to do that, but I just made life easy for you by writing it as OTS. But if somebody was interested in showing the whole thing, OSO2 and methyl, you can draw that. It's an SN2 here too, so dash line, this negative is going to attack from the front. So now you have the O ethyl on the solid line. So that's how you should solve it. Okie dokie. I think there's one more. Let's see. Yeah, the last problem is that you're given a ketone and you're treating that with a reducing agent. Other reducing agents could be LiAlH4. You could use hydrogen ranitidine, but all of these, if it's a ketone, that's going to give you a secondary alcohol. Secondary alcohol upon treatment with H2SO4 is going to eliminate. There's only one way it can eliminate. It can't go on the other side because carbon can form only 4 bonds. So this is your product. The other thing that can happen with sodium hydride and ethyl bromide is that sodium hydride will take away the H negative, is going to take away the H positive. It will generate O negative, so your species will be O negative, and then that negative attacks, Br leaves, your product would be oxygen with the ethyl, which is the same species that you will get if you treat this with the oxymercuration, remember, that we did in class, where you have the mercury and then you ring open with ethanol, and so the benzylic position is where it ring opens, and you end up with that after the demercuration process. Okay, so whether you remember this part or not, one way or the other, Williamson or the oxymercuration demercuration method, you should be able to get the answer.